Eat it every single day. Meet sodium, the explosive element that powers your heartbeat, nerves, and muscles. Without sodium, life couldn't function. Follow atomic...
Imagine an element that is so volatile that if you dropped a chunk of it in a puddle, it would just rapidly heat up, sort of dance across the surface, and violently explode.
Yeah, it's pretty terrifying to watch.
Right, but then realize that without that exact same element, your heart would literally stop beating before I even finish this sentence.
It sounds totally made up, like some kind of riddle.
It really does.
That's
But today we are jumping into a brand new deep dive based on our source material, which is a really fascinating text titled Sodium, the Vital Paradox of Reactive Chemistry.
It really is a paradox.
Oh, absolutely. So the mission for you, the listener, today is to try and understand the ultimate chemical contradiction. We want to know how one of the most dangerously reactive metals on Earth is absolutely essential for keeping you alive. Like, how can a metal that literally explodes in water keep every human alive?
Well, it's just the ultimate showcase of how much chemical context matters, you know?
Yeah.
You're basically looking at two completely extreme ends of the spectrum, but they're wrapped up in a single element on the periodic table.
Okay, let's unpack this. Because on one hand, you have pure sodium metal, which is, I mean, it's aggressive. It's really dangerous.
Very dangerous.
You drop it in water, boom. You expose it to just the normal air we breathe, and it rapidly oxidizes and just deteriorates almost instantly.
Yeah, it practically self-destructs.
Right. But then on the other hand, you have sodium compounds, like the familiar table salt you happily sprinkle on your French fries.
Which you wouldn't think twice about eating.
Exactly. You wouldn't dream of tossing an explosive metal on your lunch, but you consume sodium compounds every single day. So we have this really vivid contrast here. It's an exploding metal versus an everyday seasoning.
To understand this whole Dr. Jekyll and Mr. Hyde behavior, we actually have to look past the macroscopic explosion. We have to look at the element's atomic blueprint.
So zooming way in.
Way in, yeah. It all comes down to the architecture of the atom itself, specifically its electron configuration.
Okay, let's get into the anatomy of an explosion then. Like, what is actually happening down at the microscopic level that makes this stuff so unhinged?
Well, sodium sits in the alkali metal column of the periodic table, right? It's atomic number 11. And if you strip away the basics and look at its outermost shell, the 3s1 orbital, you find one single, highly energetic valence electron.
Just one hanging out there.
Just one. The inner electron shells are totally full and stable, tightly bound to the nucleus. But that one solitary electron orbiting way out on the edge, that single thing, makes the entire atom incredibly unstable.
I kept picturing this as I was reading the sources. It's like that single valence electron is a dangerous hot potato.
Oh, I love that analogy.
Yeah, it's like the atom is holding on to this fiercely unstable hot potato, and it is just desperately trying to throw it away to literally anything nearby so it can finally drop into a stable, relaxed energy state.
That is a brilliant way to visualize it. It wants to achieve what we call a stable octet, and holding on to that one extra electron is literally the only thing preventing it from being stable.
Wait, I have to challenge that a bit, though.
Yep.
If the whole goal is just to shed an electron, why does it cause a massive explosion? I mean, shedding an electron doesn't sound explosive to me. It sounds like static electricity.
Right, like shuffling on a carpet.
Yeah. When I get a shock from a doorknob, I'm transferring electrons, but my living room doesn't blow up.
That is a really fantastic distinction. What's fascinating here is that the explosion isn't actually caused by the electron transfer itself.
Oh, it's not.
No, it's caused by the chaotic collateral damage of that transfer happening on a massive scale. When pure sodium hits water, it isn't just peacefully handing off a potato. It is forcefully shoving billions of hot potatoes into a crowded room of water molecules all at once.
Wow, okay. And the water molecules just can't handle it?
Precisely. The sodium violently strips the water molecules apart just to force them to take that electron.
It breaks the water.
Yeah, it physically tears it apart. This creates sodium hydroxide and frees up hydrogen gas.
Yeah.
But because this chemical reaction happens so aggressively and so fast, it is highly exothermic.
Meaning it releases heat.
An immense, sudden spike of heat. And that intense heat then ignites the newly formed hydrogen gas, which, as we know, is highly flammable.
So the explosion you see isn't the sodium at all, it's actually the hydrogen detonating.
Exactly. The explosion is just the violent, fiery aftermath of billions of atoms ruthlessly offloading their valence electrons all at the same time.
That is wild. And since it reacts that violently just to shed a single electron, I guess it makes perfect sense that nature never leaves pure sodium lying around.
Never. You will absolutely not find a pure chunk of silvery sodium metal sitting in a rock out in the wilderness anywhere on this planet.
Because it already reacted.
Right. Nature already allowed it to throw the hot potato away millions of years ago. So today, it exists peacefully as a compound, mostly bound up with chlorine to form sodium chloride, which is table salt.
Which is crazy to think about because according to the text, sodium makes up about 2.6% of the Earth's crust.
It's everywhere.
It really is incredibly abundant all around us, but it's always locked in this tight molecular embrace, never free.
Which presents a pretty serious logistical challenge if you are a scientist and you want to study the pure element.
Right, because if scientists actually manage to isolate it, they can't just leave it sitting on a desk.
No, it would be gone.
The text notes they literally have to store pure sodium completely submerged under mineral oil.
Yeah, just to keep it safe.
Because mineral oil contains no oxygen and no moisture, so it acts as this liquid shield. If they don't submerge it, the ambient humidity, just the normal water vapor floating in the air of the laboratory, is enough to set off that violent oxidation process.
And when you finally look at it in that pure isolated state under the oil, its physical properties are highly counterintuitive.
They really are. I mean, when I think of a metal, I picture steel beams or thick iron plates.
Heavy, rigid stuff.
Hard, heavy materials. But pure sodium is silvery white, and it is surprisingly soft. The sources say you can take a standard butter knife and smoothly slice through a chunk of it like it's a block of cream cheese.
It's bizarre.
It really is. It has exceptionally low density, and yet it's a brilliant conductor of heat and electricity.
But this extreme reactivity brings up a profound historical puzzle, don't you think?
Oh, how we even found it.
Exactly. If this element is never found pure in nature, and it rapidly self-destructs when exposed to the basic moisture in the air we breathe, how did humanity ever discover it in the first place?
That is honestly one of my favorite parts of this deep dive. The discovery by Humphrey Davy in 1807 wasn't just a matter of, mixing the right chemicals together in a beaker.
It was much harder than that.
It was an epic struggle against the forces of nature. The chemical bonds holding sodium to elements like chlorine are unimaginably strong. For centuries, literally no chemical on Earth could pry them apart.
So he had to get creative.
He did. Davy realized he had to fight nature with a completely different weapon.
Right. He basically had to bypass chemistry entirely and use physics.
He used electricity, which was brand new at the time. Davy built these massive voltaic piles, which are essentially the world's first crude batteries, and he used a process called electrolysis.
Basically shocking the compounds.
Exactly. He took sodium hydroxide, ran a continuous, powerful electrical current directly through it, and physically forced the compound to tear apart.
Which is incredible.
Humanity literally had to invent continuous electrical current just to rip this element away from its partners. It's this massive aha moment. A technological leap in physics suddenly kicked down a locked door in chemistry.
It really reveals just how much energy is tightly bound up in those natural compounds. And by forcing it apart, Davy was finally able to see that soft, silvery white metal for the very first time in human history.
But, even before Humphrey Davy forced the pure metal out of hiding, humanity's fate was intimately tied to sodium compounds anyway.
Oh, absolutely. Long before we knew about atoms.
Our ancestors didn't know the atomic structure, but they instinctively built entire economies around it. Sodium, in the form of salt, has built civilizations, forged ancient trade routes, and driven global economies.
It was incredibly valuable.
People were literally paid their wages in salt, which actually gives us the root for the word salary.
Because before the invention of modern refrigeration, salt was quite literally a matter of life and death.
It gave humanity a way to preserve food,
Right.
drawing the moisture out of meats and fish.
Yeah, and the biological mechanism there is osmosis.
Oh, right.
See, bacteria require water to survive and multiply. When you pack meat in heavy salt, the sodium chloride creates a hypertonic environment.
So it's super salty.
Very salty.
Yeah.
So it aggressively pulls the water out of the bacterial cells, completely desiccating and killing them. That simple chemical trick allowed human beings to survive long, harsh winters and travel across vast oceans.
There is also this beautiful little detail from the text I wanted to mention. When you introduce sodium to a flame, it gives off this brilliant, unmistakable yellow color.
The flame test, yeah.
It's used in spectroscopic flame tests to identify its presence. It's just the stunning visual.
The yellow flame is a stunning visual, definitely. But if we connect this to the bigger picture, Sodium wasn't just building human society or preserving our food. It is the core architectural foundation of human biology.
It makes total sense that our ancestors instinctively valued it so highly. I mean, without it, the human machine shuts down completely.
We literally couldn't function.
So let's look at how it actively operates you. How does an explosive metal function safely inside our bodies?
This is where we examine the biological imperative of the sodium ion. Inside your body, sodium exists as an ion.
Which means what, exactly?
It simply means it's an atom that has successfully thrown away that dangerous valence electron. It already tossed the hot potato,
Oh, okay.
and by tossing it, it gets a stable positive electrical charge. And these positively charged sodium ions are the actual core mechanism behind your entire nervous system.
Wait, so it's not like the wiring in my house. Because when I think of my brain sending signals, I picture it sending electrons down a copper wire to tell my arm to move.
No, biological wiring is completely different. Your nerve signals aren't electrons in a wire, they're chemical waves. And they're powered by these things called voltage-gated ion channels.
Okay, you're gonna have to break that down for me.
Imagine a nerve cell as a really long tube. When your cell is just at rest, there is a high concentration of those positive sodium ions waiting just outside the cell membrane.
Just hovering that.
Just waiting.
Yeah.
Then, when your brain sends a signal, tiny physical gates along the outside of that nerve membrane suddenly snap open.
And because those ions are positively charged, they just rush inside.
They absolutely flood inside. And this sudden, massive influx of positive charge physically changes the electrical polarity of that specific segment of the cell process biologists called depolarization. And that tiny electrical shift triggers the next set of gates down the line to open, and then the next, creating a cascading, traveling wave of electricity that goes all the way down to your muscle.
Wait, so my nervous system is essentially just a physical flood of charged salt atoms rapidly opening and closing cellular gates.
That is exactly the mechanism. Every single heartbeat, every involuntary twitch, every complex thought you are processing while listening to this deep dive right now, all of it relies entirely on sodium ions rushing in and out of your cellular membranes.
That is staggering to think about. The exact same element that aggressively detonates in a lab beaker is acting as a tiny, life-saving biological battery inside my brain and my heart.
It completely transforms its role based purely on its context. And beyond generating action potentials in your nerves, sodium is also the master regulator of your fluid balance, which directly controls your blood pressure.
Oh, this goes back to the osmosis concept we talked about with food preservation, right? Water follows sodium.
Yes, exactly. Your kidneys are constantly working behind the scenes to maintain the perfect concentration of sodium in your blood. If you have a high concentration of sodium ions in your bloodstream, say, from eating too much salt, osmosis dictates that water from your surrounding tissues will be actively pulled into your blood vessels just to dilute it.
And more water in your blood vessels means a higher volume of liquid pushing against the vessel walls,
which naturally increases your blood pressure.
So we basically walk this incredible dietary tightrope every single day. If you consume way too much table salt, which, let's be honest, is notoriously easy to do with highly processed modern diets, you retain too much water.
Exactly.
And your blood pressure stays chronically high, putting immense mechanical strain on your heart and your arterial walls over years and decades.
But the pendulum totally swings both ways here. If you experience a sodium deficiency, which is medically known as hyponatremia, the biological battery starts to fail.
Because there's no ions to flood the gates.
Right. Your nerves physically cannot generate enough electrical charge to fire properly. You experience severe muscle cramps, profound fatigue, confusion, and in really extreme cases, total neurological shutdown.
Wow.
It requires constant microscopic regulation by your biological systems just to keep you perfectly balanced in the middle.
So if sodium ions are the microscopic batteries powering the human biological machine, the sources indicate it's quickly becoming the actual physical battery for our modern infrastructure, too.
Oh, definitely. The industrial footprint of this element is vast, and honestly, it mostly operates completely out of sight. Beyond just producing table salt, sodium compounds are an absolute cornerstone of heavy manufacturing. Take glass manufacturing, for example.
I was wondering about that. The text mentions it's vital for glass, but how does salt help make a window? It doesn't seem to make sense.
It's all about disrupting molecular structures. See, glass is primarily made of silica, which is basically sand. But pure silica has this incredibly rigid silicon-oxygen network that requires phenomenally high, volcanic temperatures just to melt it down.
Which takes a lot of energy.
Too much energy. But by adding sodium carbonate, which is also known as soda ash, into the mix, the sodium ions physically wedge themselves into the silica lattice.
Oh, they break it up.
Yes, they break up those rigid bonds. This drastically lowers the melting point of the silica, making it economically and physically possible to form everyday things like windows, bottles, and lenses.
That makes so much sense. And that same chemical utility is used in paper manufacturing to break down stubborn wood pulp, right?
Correct.
And it's essential for synthesizing soaps and modern detergents. Basically, global manufacturing would just hit a brick wall without sodium compounds.
Totally. But the physical properties of the pure metal, the dangerous ones we discussed earlier, make it indispensable in some highly sensitive, cutting-edge technological fields, too.
Here's where it gets really interesting. When we look at the future of energy and advanced technology.
Well, we mentioned earlier that pure sodium is an exceptional conductor of heat.
Right.
Because of this, liquid sodium is actually utilized as a primary coolant in certain types of advanced nuclear reactors, specifically fast neutron reactors.
Wait, hold on. Liquid sodium inside a nuclear core. Knowing how aggressively it explodes when it touches water, putting it inside a nuclear reactor sounds like a recipe for a localized apocalypse.
It sounds incredibly dangerous. I agree. But engineering is all about utilizing properties in tightly controlled contexts. Inside a sealed, entirely moisture-free loop, liquid sodium is vastly superior to water for cooling certain reactors.
Okay, why is it better than water?
Two main reasons. First, water boils at a relatively low temperature, unless you keep it under massive, dangerous amounts of pressure.
Like a pressure cooker.
Right. But sodium remains a liquid over a massive temperature range. It doesn't even boil until nearly 900 degrees Celsius.
Wow.
This means the reactor can operate at much higher, much more efficient temperatures without needing those thick, highly pressurized containment vessels.
And the second reason?
Second, water slows down neutrons, which you don't want in a fast reactor. Sodium is heavy enough that it doesn't slow the neutrons down, while still rapidly pulling thermal energy away from the nuclear core.
That is just brilliant engineering. Taking a volatile hazard and turning it into a stabilizing safety feature.
It's all about context.
And speaking of utilizing its unique properties, going back to that brilliant yellow flame test we talked about earlier, the text points out this exact property is harnessed in sodium vapor lamps.
Oh, yeah.
If you've ever driven down a highway at night and noticed that very distinct monochromatic orange-yellow street lighting, you are basically looking at sodium being vaporized inside a vacuum tube. It produces an incredibly high output of light for very little electrical energy.
It's super efficient. But if we connect this to the bigger picture, the most disruptive and exciting frontier for sodium right now is actually in the future of energy storage. We are entering the era of next-generation sodium-ion batteries.
This is a massive shift because, our entire modern world currently runs on lithium-ion batteries.
Everything does.
Our smartphones, our laptops, the booming electric vehicle market, it all relies on lithium. But lithium has some pretty serious supply chain bottlenecks.
It really does.
Right.
Lithium is relatively scarce in the Earth's crust. It's expensive to extract, it requires vast amounts of water to mine, and the global supply chains are heavily concentrated in just a few geographical regions, which, leads to geopolitical tension.
Right.
But sodium, as we established, makes up roughly 2.6% of the entire Earth's crust. It's practically everywhere, and we already know how to mine it cheaply.
So how do we actually replace lithium with sodium? Does the battery work the exact same way?
The underlying chemistry is remarkably similar. Both batteries work on the principle of intercalation.
Which means?
Well, you have two electrical poles, an anode and a cathode. When you charge or discharge the battery, you are physically moving ions back and forth through a liquid electrolyte, lodging them into the atomic structure of the poles to store and release electrical energy. Sodium ions can shuttle back and forth just like lithium ions do.
Okay, if it's so abundant and works the exact same way, why aren't sodium batteries in my phone right now? Why haven't we been using them this whole time?
It comes down to basic atomic size and weight. A sodium ion is physically larger and heavier than a lithium ion.
Oh, I see.
Because the ions are bigger, the battery can't pack as much energy into the same amount of space. So a sodium ion battery is going to be bulkier and heavier than a lithium battery of the exact same power.
And you definitely don't want a heavier, thicker smartphone.
Exactly. And automotive engineers don't want to add unnecessary weight to an electric car if they can avoid it.
But weight doesn't matter for everything.
Precisely. For grid-scale renewable energy storage, Sodium is a total game changer.
Like storing wind or solar power.
Imagine a massive bank of shipping containers sitting next to a sprawling solar farm or a wind turbine array, storing excess power for a whole city to use at night. Doesn't matter if those batteries are a bit heavier or larger because they never have to move.
Right, they just sit there.
It only matters that the materials inside them are incredibly cheap, highly sustainable, and widely abundant. Sodium-ion technology is the key to decoupling renewable energy storage from the expensive, complicated lithium supply chain.
I do have to play devil's advocate here, though, on behalf of everyone listening. What is the environmental cost of pivoting heavily into sodium?
It's a fair question.
We're talking about massive industrial applications, chemical processing, global mining operations. I mean, no miracle element is completely free of consequences.
That is a very necessary perspective.
Yeah.
The environmental reality is that managing sodium requires strict oversight. The sheer scale of industrial salt mining can disrupt local geology and ecosystems if it isn't managed well.
Right.
But more pressingly, when we utilize sodium in these massive industrial processes like paper and chemical manufacturing, we generate significant industrial runoff.
The text specifically highlights the issue of water salinity as a major problem.
Yes, and it's a compounding problem. When industrial wastewater containing high levels of sodium compounds makes its way back into rivers and aquifers, it drastically spikes the salinity of local freshwater sources.
Making them salty.
Yeah, and high salinity destroys local agriculture by basically poisoning the soil, and it devastates freshwater aquatic life. So while sodium is deeply abundant and definitely crucial for green technology, the extraction and the waste management of it still demand intense environmental responsibility. We have to meticulously manage the entire life cycle of the element.
So what does this all mean? We've traced this element from, an atomic oddity exploding in a beaker of water, to the foundation of ancient trade routes, to the literal electrical spark firing our nervous systems, and now to massive battery banks preparing to store solar power for the grid.
It is a profound testament to the complexity of the natural world and really shows how chemistry is defined by its environment.
I think we can summarize this whole deep dive with a shared thought from our source material. Sodium proves that an element's true power depends on its form. As a pure metal, it's explosively reactive. As an ion, it's essential for every heartbeat, every thought, and the future of clean energy.
It is the ultimate reminder that context is everything. The context of a single missing electron is literally the difference between a dangerous explosion and the biological foundation of life itself.
Which leaves you, the listener, with a final, provocative thought to mull over as we wrap up today. Since we've seen how context can completely transform a dangerously reactive exploding metal into the very thing that is keeping you alive and powering our renewable future right now, what other hidden, seemingly dangerous forces in our natural world are out there just waiting for the right context to become the next massive technological breakthrough?
We might just be one Humphrey Davy moment away from unlocking something entirely new.
Thanks for joining us on this deep dive into the vital paradox of sodium. We'll see you next time.